thinking about this sort of thing, so I'm fascinated to hear about these eutectic crystals, and I'd love to read out the literature. I'm adopting a very traditional scientific position in one way by assuming that by putting forward the hypothesis in its most general possible form. If I said it sometimes works and it sometimes doesn't, then it would be very difficult to test, because and it would actually be irrefutable. That's a vice and not a virtue in a scientific theory. And so I'm more inclined to think of it working, trying to think of it working everywhere. Now, there are many systems like the behavior of hydrogen atoms, the crystallization of sodium chloride, and all sorts of phenomena that physics has studied in great detail, which have happened billions of times, and as far as we know, for billions of years, even before this planet formed. So there are certain kinds of phenomena in nature which have happened so many times before, they're so deeply habitual, that they behave as if they're governed by eternal laws. The habits are so deeply entrenched. And I think many of the phenomena that scientists have studied, particularly in the physical sciences, are of that kind. And therefore they do look as if they're governed by eternal laws. Where the difference shows up is when you look at any new phenomenon, because then you can see the habits building up. With old established habits, they might look as if they're not really habits at all, but following eternal laws. So I would say that I would prefer to think of the theory applying everywhere, and I would account for the apparent non-changing of many physical habits in terms of their extreme antiquity and the fact they're so deeply embedded in grooves of habit they don't change.
Some things you simply won't be able to test.
Well, you can test the theory in any area where you can do something new. New forms, new crystals, new molecules, new patterns of protein folding, new ideas, new ways of learning. There seem to be plenty of areas it can be tested in.
Is there anything that would hard to refute your theories, or what do you consider its status of? Is it just a good idea with a few experiments? Or?
It's a hypothesis, which what a hypothesis is a guess about the way things may be. And what I've done is contrasted this guess in a variety of areas, the realms of memory, crystallography, morphogenesis, instinct, behavior, transmission of learning, behavior and evolution of social groups. So I looked at the predictions of this way of looking at things compared with the standard way of looking at things. And in every area one finds that there's a whole range of shadowy phenomena where the evidence for the conventional position is very weak indeed. And one sees that that's actually a guess too, which is in most essential areas unproved even now. So one's got one guess versus a much more common and habitual guess. And there are other guesses on the market too.
Is there anything that would falsify the morphogenetic field in your mind?
Well, a failure of experiments to show morphic resonance would falsify it, except that falsifying scientific theories is never, people often go on as if they say, Popper says the ideal is to falsify theories. I don't know a single example of science proceeding in that manner. Most scientists are trying to prove theories. And they may try and falsify theories of their rivals, which is the way it usually happens. But and it's a kind of dialectic then. Science becomes a dialectic between rivalrous rivals. And science is full of ego rivalries. Well, most people think that this is terrible vice, but actually it's one of the motors of competitive science as we know it. If somebody puts forward a theory and someone has a rival theory, and then there's the way the contest is decided is by experiment. The rules of the scientific game, experiments are usually designed to test between rival hypotheses, rather than testing a single one in isolation. And I'm putting forward a variety of tests which test between the idea that nature has this habitual tendency as against the conventional idea, which is always that nature is governed by immutable, changeless, eternal laws. And some tests may be inconclusive. Some tests may, I think, favor the idea of morphic resonance. If all the tests that are done fail it, if it fails, if it looks as if things are governed by eternal, changeless laws, that there's no evidence for any incremental change in time in any area, that everything goes on as if it were governed entirely by laws that were already there to start with, I'd find that rather surprising. But failure of these experiments would actually support that view, and the conventional view would then, for the first time, actually have empirical evidence in its favour. Because this would be the first time it's ever been challenged. And if those challenges fail, it would strengthen it. So these tests, I think, are in everybody's interest. But if they support the idea of morphic resonance, then indeed it would show that that is not a perfect model. It's the idea of a memory in nature, morphic resonance. However crude the theory is in its present preliminary form, it would be a better theory, and a theory more worth developing. And the question is the field connection in quantum non-locality in Bell's theorem and the Einstein-Rosen-Podolsky paradox, that kind of quantum non-locality, related to morphic resonance? Are they two aspects of the same phenomenon? That's the really interesting question in relation to existing physics. And nobody knows the answer. I don't know how morphic resonance as conceived would fit with quantum non-locality, which, although it does in fact involve a past, because both systems originate from a past, and it's to do with a system with a past, which is, I would say, the very existence of these particles is a kind of resonance from their own past. And I would say that there is a kind of morphic resonance link, and probably that's what it might be. But I can't fit that into the formalism of quantum theory, because I don't know it. I'm not a quantum theorist, and to work with those equations with any degree of subtlety would require a deep understanding of the subject. On the other hand, J.S. Bell, the inventor of Bell's theorem, has been in correspondence with me. He's read both my books and has sent me his latest book. So we've been in a correspondence about the possible connection between morphic resonance and his own theory. He's perfectly intrigued by morphic resonance and morphogenetic fields. And he thinks they may be connected with his own theory, but he can't see how, because there's nothing in the conventional physics which has yet proved, because it's so based on eternal equations. The idea of Schrödinger's equation is a kind of eternal Platonic form that governs all quantum processes from the beginning of the universe to the end in exactly the same way. That's the kind of inherited formalism of quantum mechanics, and that kind of mathematics, which postulates eternal Platonic type forms, is not going to be adequate for modeling an evolutionary universe. And so it's not clear how the bridge can be made, or even whether that connection, but I think there must be some kind of connection. There can't be lots of totally unconnected types of non-locality in the universe.
Rupert, why not replace the Platonic models with fractal models, and then say that time itself is the morphogenetic field? That it is some kind of fractal topological manifold and so the repetition or the connection to past states is really accomplished through resonance within the fractal, and then we have a model for resonance because it's familiar to us from other domains of nature.
Well, I don't see quite how there's a sense in which the fractal is a new mathematical model that gives us the same idea that the ancient idea of the microcosm mirroring the macrocosm. The idea of different levels.
Well, but not only different levels, but different points on the same level, in the same way that the past occupies a relationship to the future of formative anticipation, so in a fractal